All right, are we recording now? Okay, good. IR. All right, let's take a look at what we got. Where'd my coffee go? Michael, what's the base address of the GPIO? Where'd you find it?
I found it on page 18.
It's in hex? So let's look at page 18. I'm going to do this here. Page 18, page 19. Yeah, where's my mouse? All right, so if you want to know where stuff is, if you go through the opening page after all the these are IRQ numbers. What page was it again, Michael, or did you not find it? All right, take a look at chapter 5. Chapter 5 is the memory and bus system. It starts to tell you where things are located. This is the diagram that we looked at before in lecture 1. We want to know what these actual addresses are. So as I go through this, like some people found this diagram here and they said, ooh, look, let me zoom in really close and try to figure out where the GPIO is. And it says it lives there. Now, graphics are cool, but they're not sort of the most informative because is the base address like 4,000, 6,000, or is it 4,000, 7,000? So what I would use is I would come down here to this table, and you can see where all of these memory peripherals live. And if you keep coming down, your GPIO lives in this address range. So it's from 4,000 to 6,000 to 4,006 FFFFF. So the base address for the GPIO is hex 4,000, 6,000. So remember back to hex, because they're going to start to be weird letters, and that is the base address. Now, the base address just tells you where the GPIO itself lives. It doesn't tell you where any of the registers are. So if I wanted to make my pin and output, I need to write a bit to this one particular register. You need to know where it lives in terms of the base address. So at the end of every chapter, it will have a register map. And what that will say is that if you want to access port A's mode low register, you go 4 memory locations away from the base address. So the address of this is 4,000, 6,004. This is 4,000, 6,008. So those are the absolute memory addresses for those registers. And if you want even more detail, which we're going to have to do, you're going to have to look at a particular register and say, well, I know he lives at 4,000, 6,000, and I need to set bit 0 and 1 to 1 or 2 or 3 or whatever it might need to be. So you're going to need to get really good again at hex and bits and setting certain bits, reading certain bits, and modifying them. And you'll have your fill of it sort of once the semester's over. All right? So GPIO lives down here. The memory map for each register is there. So what that means is that if you wanted to talk to a particular register, it's the base address plus the offset. Base address, offset. So that means that port E's mode L register lives exactly at that location. This is like a fundamental thing you have to understand for this course, and if you don't understand it, you're not going to be successful. Questions? Okay, because you're going to get really good with pointers. One thing you might have seen in the memory section is something about bit banding. You will see that in other sections. Bit banding just means that the memory addresses of every device are aliased in another band for faster access. So remember how there are multiple buses on the Gecko? Each device has a different address depending on which bus you want to access it on. So there's like the highway and then there's like the fast way. So if you want to access things quicker, you can use its bit banded address. All right? What we're going to get into here is going to be crucial for what we're doing the rest of this semester. And it's putting that memory mapped I/O into practice. So let's say you know what register where it lives, and you know what bits you want to set in it. How the heck do you set random bits in a memory location? You've never had to deal with memory explicitly when you've been programming. If you're in Java, memory doesn't exist and data collection does it for you. If you're in C++, you do new, you do delete. Some variables are on the stack, some variables are on the heap. You don't actually care where they live. In a microprocessor, you really do care where your variables live, because those are the locations of the peripherals you want to talk to. So the technique that you use is you take a pointer and you make the value of that pointer be the address that you want to talk to. Because remember, a pointer is a variable that contains an address. When you dereference that pointer, you go to that address. So if my pointer contains an address of a place I want to talk to, and I dereference that pointer, I am now talking to that register. I am talking to that peripheral. And you read and write from it like you would any other variable. Except the data doesn't go to RAM, it goes to a peripheral. Two important things about this. One is that when you declare these pointers, they need to be declared volatile. And volatile is a special keyword that tells the processor and the compiler, do not cache this value. Make sure every time you read it live. Don't pull it from the cache. The second thing is that we want to be crystal clear about the size of our variables. This explicitly declares this as an unsigned int of length 32 bits. So in this course, you will not see ints and unsigns and longs. You will see uint 32, uint 8. We actually won't do anything signed, so there will be no int 16. What this says is that this object should point to something that is an unsigned value of 32 bits long. The size of your variables have to explicitly match the size of the space you want to read. Because if you take an 8-bit pointer, if you read from an 8-bit pointer, you're only going to get the lower 8 bits. Or it might interpret the address as only 8 bits long. You'd have to figure that one out. Either way, it's bad. Volatile is important because you want to make sure that you read it and it doesn't get cached. Normally, the computer tracks what writes it makes to memory and what reads it makes from memory. So a lot of times, your processor is going to go, well, I just read you that memory location. I'm not going to do it again because I know I haven't written to it. Which is fine when there's only one thread and one process. But your I/O might be changing state because stuff might be happening to it externally. So you need to read it again and not assume that the value is simply going to be cached. One other thing, you should see this UL there. That should look weird. It should look weird because the way that we're going to do our variables is that we need to be explicitly clear with the compiler how long of this number is that I'm typing into you. And by saying it's an unsigned long, it tells it that it is an unsigned 32-bit value. This is a compiler directive. Otherwise, it may interpret this as a signed number depending upon the address. And then you end up at the wrong location entirely. So, 2 rules with pointers. Make sure they're volatile. Make sure they're the correct size, both in terms of the type of pointer and the address that you give it. To be able to talk to these peripherals, you need to be able to read from them. And it's really hard the first time you boot up a processor if you just start writing bits out into space. You have no idea if it's going to work. Like if I'm configuring an I/O to blink and I write a lot of bits to it and it doesn't blink, did I configure it wrong? Did I write to the correct address? Like you have no idea of sort of knowing if you're even doing the reading and writing correctly. So an easy way to get used to reading arbitrary memory addresses is to find something in the processor that is constant. So every sensor, every chip is going to have some sort of memory location that has something like a product ID or a code number. And the first thing you want to do is to make sure that you can read that code number out, and then when you read it, you know that you're actually doing your reads correctly. So with this Gecko processor, we're going to start by doing reads to 3 known locations. So inside of the processor, there are 4 actually memory locations that have constants burned into them, meaning that at manufacturing time, at these memory addresses, it burned in certain values. So if we read from these addresses, we should be able to get known values. So from here, we should know how much flash we get, and I think we have 128K of flash. You can go back to lecture 1 and look. So if I read from this address, I should get the number 128, represented in binary. Here, RAM, we got 1024 of RAM, and this is done in kilobytes, so we need to make sure that we read the size of the RAM. The part number, this is a 990. So if you read from this address, you should get the number 990. This is a giant Gecko, so when you read from this address, you should get the number 72. And the way that this is going to look, and the way that you're going to do it in code, and this is sort of the style I want you to follow, is I want you to use a pound defined to specify the address. So above your main function, do a pound define, give it a name, give it the address. Express the address as a 32-bit hex value, making sure that it's unsigned. Write it all out. It'll make all of your columns like the same length. It'll look nice. Then in your code, you're going to make a volatile pointer of 32 bits. You're going to then take that address and cast it as a 32-bit pointer. So what that does is that makes an object that contains an address, and then when you read that object, it will pull the data from memory. So the way that this would look in practice is that I would take my RAM size pointer, I set it equal to the address, I read the value out into another variable, and if I was going to write back to it, this is what I would do. But it won't do anything because that's a read-only address. As we get into the GPIO, we're going to do sort of more complicated things, but we don't need to be there yet. What I want to do now is I want everyone to actually write this code, and we're going to take 5 to 10 minutes to do this. What I want you to be able to do is to get pretty good making projects and slapping down a quick bit of code such that you can access these things. So if I pull Simplicity Studio up, let's see if I can pause you. Hello, computer. Can't be paused. stop it. All right, I'm just going to take this off then. All right, remember, grab your gecko boards. And the quick and easy way to make a project, if you remember, so you take the board, got the wrong cable on it. Not a great thing. It's just something to do. So this is, to Travis's question, this is not a graded thing. It's just something I want you to do sort of in class. This won't really extend beyond 5-10 minutes. But the easy way to make a project, the way I always do it, is if you click up here on J-Link, you click on your board, you come up here, you go to New, Project, and then for some reason there's a difference between this Silicon Labs button and this Silicon Labs button. I have no idea why. But if you click the lower one, you should get something here that says EFM32 Giant Gecko. And if you click Next, we'll do an empty C++ project. And let's just call it read memory, just for fun. And I'm going to link all the sources. So now I've got my very, very basic project here. And what I want you to do is to come up here. So I said link sources, and I just made everything link to here. So make a pound define statement, and let's say that you want to, the RAM memory address. And that one happened, or the RAM size, that happened to be F008 1FA. And that's the address, and then I'm going to add UL to make sure the compiler knows it's an unsigned long. I'm going to come down here and I'm going to make a volatile uint32t pointer called pointer. I'm going to cast it to that address. All right? It's a lot of stuff. It's a lot of stuff. To make sure I got the address right. FE08 1FAU. All right. Now that you've got this in your program, what you can do is I'm just going to put a dummy variable here so I can have a breakpoint. I'm going to put a breakpoint there, and then I'm going to debug my program. What you should see under variables is you should see that there's my pointer. The value of my pointer is the memory location I want to read. I need to dereference my pointer to actually get the value. So you can just dereference it by clicking there. And it's going to give you a value as a long unsigned int, which you're going to need to translate into another value. Or you're going to translate it into hex. So what you can do is you can take all of these addresses and you can read them out. So do all three of them, write down what you get, and let's see if everybody gets the same thing and reads the same numbers. And I will put this back up so you can get the memory locations that you need. So let's take 5 good minutes doing this. Really do this. Really get used to it. Make sure that you're actually reading from the memory locations. it's always going to be catching up. Two. We got 31. The easiest one to figure out is the part family. And we'll walk through Kevin. No, that's a part.
No, I mean, so
When you created the project? And then, so somehow when you made this project, you picked the wrong. Like it should automatically be there when you start the project. Like don't go through a menu list and pick your part. It should automatically be populated. So this project will automatically do it. So what I would do is close it.
So then you make something different from family.
Project. Let's do this one. Okay, so that's not it. Let's do this one. So okay, was your board plugged in when you turned on the? So let's kill this decision and bring it back up.
This is also like variables.
So they're not. So here's the fun bit. For Flash, you're reading the lower 16 bits, RAM 16, RAM 16. The part family is only 8 bits. So if you're reading from these memory locations, you're going to probably get a giant number. It's going to be many millions of millions. You're not looking at the entirety of the number. For the part family, you're only looking at the lower 8 bits. So on my system here, for the part family, put this back on. So for the part family, I read out in decimal, 429490488. All right, that's what I read out for the part number. I was hoping to see the number 72 because that means it's a giant gecko. The number 72 doesn't live up there. That's a 10-bit, that's a base 10 value. If I take that number, this number right here, and I put it in my nice little Windows calculator, and I turn that into a hex value, what this becomes is 0xFF9748. I still am not seeing the number 72 that I hope to see, but I'm only supposed to be looking at the lower 8 bits. Still with me, Travis? Hex 48 is 72. All right, so let me roll through this again. Come on, Peter. When I read this memory location, this table tells me that if I want to know the part family in bits 7 through 0 of that register, I'm going to look for a certain number. The number I hope to see is 72. The reason I want to see 72 is because I'm using a giant gecko processor. I made a pointer. I read out the value of that pointer, and it turned out to be 429 million. That's not what I'm looking for at all. But you're looking at this in terms of decimal. Look at it in terms of hex, and then look at only the lower 8 bits, which are the ones you care about. The lower 8 bits is hex 48. Hex 48, when written as a decimal, an integer, is 72. Get used to that sort of mind-numbing in your head, because you're going to be reading out these values, and you're going to need to be able to switch between integers and hex. And honest to God, the easiest way to do that in mass is to punch it in the Windows calculator and tell it to go from decimal to hex. Like, I don't need you to do this by hand. I already quizzed everyone on that 2 years ago. But the important part is my debugger here is going to show this to me in ways it thinks I want to see it. It's going to show it to me in human readable format. And you can right-click on your variables and you can change how they are represented to you. You really generally don't care about decimal in this class or integer. So when you're reading a configuration register, you're going to want to read that the part value here in hex is 48, and 48 turns out to be decimal 72. Who's okay with this? Who's got some difficulty with this? What's your difficulty, Kevin?
I'm still not reading the thing.
Okay, so we got to get you on the right project.
Yes.
Okay. The trick that you're going to need to get used to is that you're not going to necessarily read a value and the exact variable that you want is there. It's going to be embedded inside of the bit fields of the different things. So I don't have 648 million bytes of RAM. I need to change this value back into hex, and then I need to read out the upper 16 bits. So if I just go, which is 80, which means, yes, I have 128 kilobytes of RAM. So you may look at this initially and you may say, well, 80, that's not the answer I want. Well, that's hex 80, which is a different value in decimal. Kevin, you're kind of staring at me. Michael, Joe, good? Or Ben is, sorry. All right, we will keep going on from there. Where are we at? This is how you do the reading. This is how you read the variables. You can also, in the same way, write data out as you would. But we won't necessarily do registers because they don't contain anything useful. What we're going to start doing is you're going to start building your own pointers that go to the same registers that you want. And the easy way to do this is to define the base address as a pound define the offsets in your text, and then if I want to talk to a particular address, I have the compiler calculate it for me. So these are some compiler directives that will automatically do some math for you, so inside your code you're not actually adding up all of the addresses and all of the variables. So for the lab that's going to come up, probably after Wednesday, you're going to be talking to the GPIO, and you're going to want to implement this sort of structure to automatically get the registers that you want. Important things when you do this, though, again, is the UL and the parentheses. If you don't do the parentheses, because a pound defined is a copy and text replacement. All it does is it takes a string and copies in another string. And so if you don't have the parentheses, then the text will get copied in and it won't be recognized as a mathematical operation. So you do need the parentheses to make sure that when that text replace occurs, it occurs with the right values. Okay. You found the pointers. You know how to talk to a memory location because you can set a pointer up to it. Now you've got to go about the task of figuring out, if I want to configure a GPIO to do something, what do I need to do? So the four important registers that we talked about were data in, data out, control, and mode. So we had those on the big diagram, and those are all described at the beginning of chapter 32. Not only do you need to know the registers that you need to modify, you need to know the values that go in those registers. So you're going to have to look up the data sheet and you're going to have to say, all right, I want to change the control register. What do I want to change it to? So there's control, there's mode, and then there's data in, and then there's data out. Try this as an example. You want to set pin PE2, so port E, pin number 2. If you want to set that to a high output, what registers do I change and what values do I put in those registers? So go to the end of chapter 32. For port E, pin number 2, what explicit and exact registers do I modify to make these configuration changes? Each register is going to have a little description on it, and it's going to tell you what all of the fields are. So here, this is the start of the description. It's going to say, so port GPIO PX, because there's going to be a PA and a PC and a PD. They're all going to be at a different offset. But for all of the control registers, I have 2 bits here that I can configure. If I want to configure this port for standard low, high, or low drive mode, I set those corresponding bits for that port. For my particular pin, I need to set its mode. So each pin has 4 bits of mode configuration that you can set. So if I'm setting pin 0, I am configuring these 4 bits. What value do I write in there? You write in the value here that sets its mode that you want. So go look at chapter 32 and the end of chapter 32. Figure out what you've got to set in all of these different ports to make PE2 a high push-pull. Download give me the names. Give me the names of the registers, guys. Just give me the names of the registers. Kind of break apart what I said. PE2. Okay, that's a keyword. Am I on port A? Am I on port F? Am I on port Z? I want my output. I want it to be an output. That means it's a push-pull. How do I set something to be a push-pull? I want my output to be high. How do I make it high? So what mode do I want? So this mode register sets the mode. This output. A lot of different ways you can do it.
This is a different register than this one?
This is the control register.
Okay.
This is the mode L.
Okay, I was going to say, good to know that the rate that different to do that.
This is a different functionality. This is the drive circuit. Yep. Yep. So this register goes at 0 offset. This register goes at 4 offset. Yep. So each will enter there is a different register that lives on its own and you can configure. They all work together to configure it how you want. Then good. Okay, so when it's PE, what port am I talking about? Okay. Because all of the ports have a mode L register, it's not going to repeat this 5 times. So it's going to say X here means all. So that means, so you can say GPIO port E mode H. Like that's the name of the register you need to start. But all ports have that exact copy of that register for their own port. So they're only listed once. So what that means set only a certain field. So be very specific about what bits you set. If you write 0 to register control,
Yes, I understand this. So we should want to set that to a binary code.
yes.
Because that's
No, the user is just
oh.
yes.
So you said we're setting 4 bits.
But if you write 0, 1, 0, 0 to register, what it's actually going to do is it's going to write 0, 1, 0, 0. It's not in the right spot. We'll get to that. All right, let's take a look. Let's take a look at these registers. This is your confusing introduction to how all of these things are configured. First things first, you've got control, mode, data in, data out. If you look on the map here, every single port has its own control, mode, data out, data in register. They're only going to describe it to you once in the documentation because every port has a copy of this. So port A's control is at 0 offset and port B's control is at 24 offset. It's the same functional register but for a different port. So we know that we need to do control. And so what you can do is you can come down here to control and you can say, well, what do I want my drive mode to be? So if you want to set control, that would be port E's control. And you can set it to sort of whatever drive mode you want. And I think I said standard, it doesn't really matter. You're going to set this register to be 0. By default, it's already 0, so you don't have to do anything. You should notice that on each one of these lines, it says what the reset value is of the register. So that's what the default value is of the register. And it also tells you whether it can be accessed as a read or write. Question, Bill? Okay. Ben?
So that's the port configuration for all pins?
Yes. All pins on a port are governed by the same drive mode. All right? So this would be port E control, then it's drive strength.
So 16 pins?
There are 16 pins in a port. You have 5 ports, so each port has its own drive strength. So select drive mode for all pins on port configured with alternate drive strength. So they have a standard drive strength, but if you enable alternate, that's what governs it. Other questions? Okay. Now you need to set the mode. There are 2 mode registers. There's mode low and there's mode high. Low and high doesn't mean better or worse. It just means that mode is a 4-bit value. So with 16 pins, that means there is 64 bits of configuration data for the mode. Your registers are only 32 bits. So you need a low register and a high register to configure all of your pins. The low register controls pins 0 through 7. The high register controls pins 8 through 15. So if I'm dealing with pin 2, is it going to live in the low register or the high register? The low register. So I'm going to set PE mode L to some value. Now, this is where it gets tricky. Mode, the configuration for pin 2, lives in bits 8, 9, 10, and 11. Okay, it's a 4-bit value. If I want it to be a push-pull output, then what this table is telling me is that I need to write decimal 4 into that location. Decimal 4 is, well, hex 04. If I did what we did in class earlier, and I made a pointer to this register, and I said pointer equals 4, what bad thing happens? So if I write mode equals 4, does my 4 get written here or here? It gets written here. So what we will see when we come back Wednesday in the lecture is that you generally never ever say register equals number. Because when you say equals, you are overwriting the entire contents of the register. So if I wrote mode L equals 0, then I nuke all the configuration bits of all the registers. What we're going to see is that we're going to do a lot of shifting of values, and we're going to do a lot of ORing of values. So if I took my 4 and I shifted it by 8 bits, now it's here. And then if I OR it in, it copies it in. So we're going to talk about shifting and masking in the next lecture. So for the sake of completeness, I'm going to say that bits 11 through 8 get set to 4. To be very explicit about which bits get set for what reason. Joe, I wanted my port to be a output. Do I care about the data in register? Nope. Don't care about it this time. Final register is data out. There are 16 pins per port. That means the lower 16 bits govern the output state of the port. And so I want PE out or D out, bit number 2 to be equal to 1. So if I write D out equals 1, I'm going to put a 1 here. That's not what I want. I want to put a 1 here in the right spot. So refamiliarize yourself with registers, with bit fields, with hex. That's how we're going to kind of read and write a lot of our configuration values. In the same way that if you naturally looked at this part number and you go, well, I was supposed to be C72, why do I have 429 million? You have to look at the correct bit field to get the value that you want. I don't expect you to nail this right now. Bill, yeah. Okay. Okay, so this is a good question. Let's say that I truly wanted to talk to PED out. Okay? I actually really want to talk to this. Then this address would be the GPIO base address plus the offset. So that means that this register is at 4,000, 6,000 plus, what's the offset up there? C? Okay, that means that this register lives exactly there. You're right. All right. You're right, Bill. My bad. We go back up to the table. So we wanted PE out. My bad. All right. So it's not simply C. It's 9C. For any arbitrary port, it is C off of where the port starts. That means it is 9C off of the base address of the entire GPIO range. It's a lot of looking up tables and doing that. Jason. It says C because it's relative. Every GPIO looks exactly the same. And so the way that the manufacturer does is they make one GPIO module and they, boom, plop it down. Then they, if you want more GPIO, they go, boom, and they plot it down. So from the origin of wherever your GPIO port starts, its D out register is always C away from where the port starts. Now, you want to know where the port starts, you look at where the GPIO itself starts. So, yes, this information here where it says offset, not as useful. So I can see some of you, when you do the lab, you're going to look at that and you're going to go, aha, it's 0 away. It's 0 away from where its own port starts when you read that number. This is, let's say, the absolute offset from where GPIO starts. So this exact register is 9C away from the start of here. It is C away from where port E starts. That's how it all sort of works. And they do it very logical and very orderly, such that you can like write header files and compile, and it runs through. I don't need you to have this nailed down right now. We'll do more of it on Wednesday. But you're going to need to get good at it, because every single peripheral we're going to talk to, you're going to have to go through this process. And I'm going to make you go through this process, because if you can learn how to do this for one processor, you can do it for any processor. Because every single one of them is going to be a memory-mapped peripheral system. And they're all going to have this exact thing, and they're all going to have their own bits. And so if you can do it on this Gecko, you can do it on a Teensy or an Atmel or a PIC or whatever else you need. It's just going to be different numbers in a different system. All right. We will stop there, and then when we come back, I will go over every single little bit that you need to set, and we will do examples of how to actually modify these things. Darren?
So I guess my question is, we don't actually have to write out the addresses of the registers we want to change. Can I reference it by the name that's in the data sheet?
Yes and no. So, by default, with no help, yes, you have to write out every pointer. But the manufacturer has also done that for you, and there will be data structures. There will be data structures that they provide that allow you to reference. There will be data structures that they provide that will allow you to automatically reference the register. So what we will get to, and what we'll get to on Wednesday, is actually this. They have made a GPIO data structure that exactly it maps the data structure exactly to memory. So if you access fields in that data structure, you're accessing memory. I want you to do it by hand first. After you do it by hand for the first lab, then you can use these to your heart's content, because it's just a waste of effort for you to calculate pointers every time. But the first time through, you're going to do it. So this is a data structure that exactly follows the memory layout, and we'll talk about how they make that data structure live in memory at the right location. So yes, I was doing something for embedded systems, and I needed to access a certain port. Atmel already has a data structure with that port's exact name, and so I can just read it like I would any other variable. It's super helpful. You still have to do all the bits and the shifting and masking, but any manufacturer is going to provide you some header file that gives you access to these structures quickly. They're also going to give you libraries that'll do this stuff quickly too, as we'll see on Wednesday. But what happens when no one gives you libraries, or then the libraries conflict with other things, and then your project doesn't work, and that's super fun. Okay, we have an hour left. What I want to spend on that hour is I want to make sure everyone is working on assignment 1 and is getting through assignment 1. It's due to me before class Wednesday, so you've got 48 hours or whatever to get that done. It really shouldn't take an hour. It should take an hour or two once you sit down and bang it out. The assignments are meant to help you prep for the labs. The labs get you through the course. The assignments also prep you for the exams. That's kind of what your homework's like. Anything else? All right, I'm going to turn off Mr. Robot.